Hi guys, I've collected these two questions from the years October 2021 and October 2022 for Unit 3. These two questions are mainly concerning the rate of reaction and specifically the initial rate of reaction concept and calculation. First of all, in this question, it's talking about an enzyme called bromelain that breaks down proteins such as casein. Name the bond between amino acids that is broken down by this enzyme, and it's definitely gonna be peptide bond. This is the type of bond that joins amino acids in primary structure. Name the process that breaks down the bond between amino acids. It's gonna be hydrolysis. Any breaking down of a bond is hydrolysis, whereas the formation of a new bond is condensation reaction. Let's get into the part concerning the rate of reaction. The digestion of casein by bromelain was investigated. The amino acids in casein, a milk protein, were stained blue. 4 concentrations of this casein were used. A colorimeter was used to measure the absorbance by the blue amino acids released in this reaction. The more digestion has occurred, the more blue amino acids were released and the higher the absorbance reading on the colorimeter. And these are the results of this investigation. We have used different concentrations of casein of 3%, 2%, 1%, and 0.5%. All these concentrations show me a different absorbance of the blue color. Where the idea of this question is about the increase in concentration of the blue amino acids produced from digestion of casein, this milk protein, and this is gonna increase the absorbance reading, where the concentration of these amino acids is gonna increase due to its digestion. So as we can see here, that the higher the concentration of this protein, the higher the absorbance of the blue amino acids, and this quite makes sense for now. This table shows us the initial rates of reaction, which can be obtained from this graph. The table shows the initial rates of this reaction. Complete the table by calculating the initial rate of reaction when a 3% concentration of casein was used. So here we're going to find the initial rate of reactions for all the concentrations except for the 3% concentration. So how do we actually get the initial rate of reaction? This is going to be through the gradient of the line, but not just the gradient of the line at any point. It's specifically at the initial part of this graph. So the initial part of this line would be in this area between 0 and 50. It's this straight line right here. So I'm gonna draw a tangent if it was a curved line, but here I don't need to draw a tangent. I can only get the gradient through this straight line. So maybe in this 3% casein concentration, I can get the point from the x-axis here, which is 50, and the point here, which is 0.9 on the y-axis. So I can simply get the gradient by dividing the value here on the y-axis by the value on the x-axis. So it's simply going to be 0.9 divided by 50. This is my gradient and my initial rate of reaction. This results in 0.018. So you're just going to write your answer here. You can fill it in the table. And let's continue. And now we're asked to plot a suitable graph to show the effect of substrate concentration on the initial rate of reaction. As we've learned before, that the left side of the table represents my x-axis, whereas the right side of the table represents my y-axis. This is just the basics of plotting graphs. So I can start with setting my labels. And now I've labeled my axis, where the x-axis is the substrate concentration and the y-axis is the initial rate of reaction. And don't forget to add your units here and there. Now we can set a suitable scale for the x and y-axis. Looking at the substrate concentration, it could be 1, 2, 3, 4. This is a great difference between them, and it's gonna help me fulfill all the points required, and also fill up a large space of the grid. So you can start with the 0 here, and the y-axis could be looking at the ranges of the initial rate of reaction. We can make it starting from 0.004 and ending at maybe, for example, 0.02. So this is my maximum point, and I get a point below this one by 0.004. Let's try to put it on the y-axis. If I started with 0.004 and it kept increasing by only 0.004, I'm gonna end up with the correct range. Okay, and now we've filled the scale correctly. Let's start plotting the points. First one is 0.5 and 0.008. Here is my 0.5 and the 0.08 is here, so I can just draw an X here. And the same goes for the other points. And here's how the plots look like. We can just join them with a straight line using your ruler, of course. Now let's continue with solving the other questions. Calculate how many times faster the initial rate of reaction is for a casein concentration of 2% than a casein concentration of 0.5%. So do I actually have these in my table, the 2% and the 0.5? Yes, I do have them. I need to calculate how many times larger. How many times? Times is a key word that I need to divide to get the answer. So divide the larger number by the smaller number. 0.014 divided by 0.008. The answer using the calculator, it's gonna be 1.75. But take care that the question is asking you for two significant figures, so we can round it up to 1.8. And pay attention that if you actually wrote this answer here, you're gonna lose the whole mark even though you know how to calculate it. So writing the correct number of significant figures as asked, it's really important for your mark to be awarded. Next, we've got an explanation question. Explain the shape of the graph you have plotted in question II. And as we've come to the explanation part, as the substrate concentration increases, we are finding that the initial rate of reaction is also increasing. And why is this? It's because there is more substrate, so more collisions and more enzyme substrate complexes are formed. I guess that's really basic information based on what you've learned in O level and in A level, so it's really basic for you to understand this. And we have to say that it does not level off here. There is no leveling off because the enzyme concentration does not become limiting. It's not limiting yet. So the active sites of the enzyme are not all occupied at the highest substrate concentration. We can write this here in the way that you like, but it has to include the keywords. So first of all, even though it's an explanation question, I have to describe the graph first in a simple general trend description, that the rate increases as the substrate concentration increases. Next, we can start explaining this graph. So now I've described a general trend description of this graph. Then I explained that there is more substrates, more collisions, and it doesn't level off because the enzyme concentration does not become limiting. Part C in this question is talking that Bromelain can be used to prevent apple juice from going brown. It can be extracted from the stem and from the fruit of the pineapple. The effect of pH on these extracts was investigated. So the pH here is the independent variable. The graph shows the results of this investigation. And here the graph is plotted and everything's ready, but it's asking for us to draw a suitable table to show the results of this investigation. And we know now that the pH here is the independent variable. The one on the x-axis is the one on the left side of the table. And the enzyme activity for both stem extract and fruit extracts are on the right side of the table, yes? So let's draw a suitable table. The pH goes on the left side and the enzyme activity goes on the right side. Don't forget to add the unit. This is for the stem and this is for the fruit. And I'm gonna extract the data from this graph into the table. So this is my final table, and let's see the next question. Determine which of these extracts is most useful for preventing apple juice from going brown. Let's get back into understanding the concept of this part C in this question. And according to this table, the stem extract, it has over all pH values, it has a higher enzyme activity. And why does a higher enzyme activity make it more useful for preventing apple juice from going brown? Because this enzyme here was used to prevent apple juice from going brown. So if this enzyme was more active, it's gonna do its action more effectively. It's gonna prevent the apple juice from going brown more effectively and efficiently. So my answer here is definitely gonna be stem extract. And why is that? Because it's more active and it has a higher enzyme activity than fruit extract at all pH values, and we can use data manipulation by stating how many times it is more effective than the fruit extract. Let's put this answer into words. And for the data manipulation, we can go to the table here and say, for example, in pH 8.5, the stem extract has a higher enzyme activity by the subtraction value of these two numbers. So if I subtracted this by that, it's going to be 4.1 AU, more active than the fruit extract. So I'm just going to write this value in my answer as a data manipulation point.